So, welcome to the UniChem webinar. The full title for this webinar is An Introduction to UniChem, EMBL-EBI's mapping tool for small molecule database identifiers. So my name is John Chambers. I'm joined by my colleague Anne Hersey, and we come from the ChEMBL group based at the European Bioinformatics Institute, or the EBI as I'll refer to it from now. The EBI is based near Cambridge in the UK, and we're part of a larger pan-European organisation called the European Molecular Biology Laboratory. So this is the plan for today's webinar, and you'll see this slide coming up throughout the next 30 or 40 minutes, so you can get an idea of where we are in the webinar. I'm going to start by jumping straight in and telling you what UniChem is and how you can use it, and how people have used it. Just 3 or 4 slides on that, and then some background. I'll jump back in time and 3 or 4 slides just to describe why we developed UniChem and what problem it was designed to solve. Then some requirements and features, the data model and the principle we use for normalizing structures and so on. And then we'll talk about the current content, the sources that we have, the downloads which are available to you, and various stats and analyses. And then for the last third or half of the talk, I'm going to talk about an extension to UniChem which is called connectivity search. And at the very end there'll be an opportunity for Q&A. So, first section, what is UniChem? So many resources on the internet which have small molecule information within them have pages specifically for individual molecules within those sources. So for example, the ChEMBL resource here, this is a page for ChEMBL-12, the compound ChEMBL-12. Hanging off that page is all the information relating to that compound in ChEMBL, including all the bioactivity data and so forth. But if you were to scroll down to the bottom of this particular page, you'll notice that there are a series of cross-references to the same molecule existing in other resources. These links, these cross-references, are automatically created by UniChem Web Services, and this is the purpose of UniChem, to create these links automatically on the fly as somebody opens a page for a specific compound within a resource. Now, other resources can make use of this same functionality, and we invite people to do that. People can wire UniChem up to create these same hyperlinks in their own resources, or they can use UniChem as an analysis tool if they wish to create the same sort of information as part of an analysis. To do this, there's all the information that one would need to create the web services under the web services page within UniChem. I'm not going to describe to you here the process of creating a web service client for yourself. There's many different ways of doing that. But this page will describe to you, in essence, how you create the RESTful web service request, the URL, which you see at the top of this slide here. In essence, this is the request that is made to UniChem and creates the links which you saw in the previous pages. You can, if you want to, simply put this URL into a browser, and most modern browsers will allow you to see the results of such a query, as shown in this slide here. You can create, yet again, the same query by using the UniChem interface. If you go to the home page of UniChem and put in the term ChEMBL-12 and then select the source as being ChEMBL and then hit query, you will retrieve the following data set in a table. And this is essentially the same data set as we saw 2 or 3 slides ago. There's a little bit more information on this slide. So if I go through it, you'll notice in column 3 there's all the IDs from the different sources that UniChem creates, which are also assigned to the same structure as the query structure. So for example, DB00829 from Drug Bank is currently assigned to the same structure as ChEMBL-12 in ChEMBL. But you'll notice also that the row beneath that one I just mentioned, which is DB07699 in Drug Bank, is not currently assigned to that same structure, but it was once upon a time. And in the fifth column along, the LR column, this indicates when it was last assigned to that same structure. So UniChem is also acting as a bit of an archive for data ID assignments. So I'll just jump back into why UniChem was developed. So at the EBI, we have several resources which contain small molecule data. And all of these resources evolve at different rates and in different ways in response to their user communities. And we predict that in future new ones will be developed and adopted. And for example, the EU Open Screen database ECBD, we hope to host at the EBI very shortly. So the question really for the chemists approaching the EBI databases is how can a chemistry-centric user make use of all these data? How can they search for them? Well, an obvious way would be to accumulate all of the information into one large database, which is clearly an impractical way to proceed and would involve a large maintenance burden. So instead, we've decided that at the EBI that these resources should remain independent and be allowed to evolve independently, and that links, hyperlinks, should exist between them. But prior to UniChem, the maintenance of these links was very time-consuming and involved a huge duplication of effort, because each of the separate sources had to create the links themselves to all the other resources. So the principle behind UniChem is that we abstract out this process into a single centralized process, where the maintenance overhead of creating these links is shared by everybody. We also realized when we'd done this, of course, that it's a very short step then to pull in equivalent data from external sources, which we did. And then another small step to actually make the mapping service open to everybody so that everybody can take advantage of this linking process. So, requirements and features. The essential requirements for UniChem are, of course, that it must create these cross-references between chemical structures and their identifiers, but it also has to be fast. It has to be capable of producing these mappings on the fly during a web page load. It has to be low maintenance, and it has to be up to date. And we have to some extent, archive and track changes of ID to structure assignments over time. So those were the main principles that we worked to when we designed and built UniChem. A very, very early design decision was to try to select a principle for normalizing compounds, a standard which we could use to say that one structure in one source was the same as a structure in another source. And we decided upon the standard INCHI as this normalizing mechanism. The INCHI stands for International Chemical Identifier. The reasons for this are that it's non-proprietary, free. It's not a registry system, so we don't have to send the structure off and then wait for an ID to come back. It's specifically designed for printed and electronic systems, as data sources. And the hashed representation, which I'll show you in a minute, aids a private querying. So this is the detail of an INCHI. It's the long string beginning with INCHI in the middle of this slide, and this is the INCHI for the structure that you see just above it. The first thing you'll notice is that the INCHI itself is divided up into layers separated by forward slashes, and layers to the left are simpler representations of the structure. So on the far left we have just the molecular formula, and then the next layer is the connectivity, the way the atoms are actually connected together. And then subsequent layers deal with stereochemistry and isotopic variance and protonation states and so on. So the hashed representation, which you see beneath, is and is called the INCHI key, is a 27-character fixed length string, all of capital letters and hyphens, which is created by a hashing algorithm during the formation of by the INCHI software. Most importantly for us today, you'll notice that the INCHI key itself is divided into sections, and the first 14 characters, so-called connectivity block, or the first INCHI key hash block, FIKHB, which I've shown in blue, this is created by a hash simply of the first few layers, the connectivity layers So these, in essence, simply encode the connectivity of the INCHI. So two structures differing in stereochemistry but with the same connectivity will have the same first INCHI key hash block. So this is the data model for UniChem, and normally I'd hesitate to put up a schema in describing an application, but I think in this instance it is particularly useful because it is very straightforward and simple, and once understood you'll understand all there is to know about UniChem and what you can get out of it. So in essence it consists of four tables, two large tables, the structure and cross-references table. The structure table is one large list of the standard INCHI, the structure, together with the standard INCHI key. And once structures go into there, they stay there, they never come out. The cross-references table is simply a way of assigning a particular compound ID, such as ChEMBL 12, from a particular source, SRD ID 1 in this case, to a particular structure via the UCI, the UniChem identifier key. Sources are denoted by an SRC_ID, which is the primary key of the source table, and a fourth table, release table, simply tracks the releases of all the different sources. Another field in the cross-reference table which is worthy of mention is the assignment field. This can either be 1 or 0, 1 indicating that the assignment of that compound to a particular structure is current, or 0 if it's obsolete. So using this model, it's probably quite straightforward, I think, to understand how UniChem can track historical assignments. Suppose we have a data source S, which releases data once a month, and within that data set, compound 123, over the course of 3 months, changes the structure to which it's assigned to, INCHI X, INCHI Y, INCHI Z. Those three green lines that you see there are, in essence, separate records in the cross-references table. The first two will currently have an assignment of 0, and the last one will have an assignment of 1. So in this way, UniChem keeps a record of current and obsolete assignments. Similarly, UniChem can deal with multiple assignments. So either multiple compounds all assigned to the same structure, or a single ID assigned to multiple structures. Again, these are dealt with in the same way. Each of these green lines here represents a separate record in the cross-references table. There are a few loading rules required just to keep the integrity of the database sound. So we just do a check, because when we draw data from a source, we draw the INCHI and the INCHI key if they're both available. But we don't take it for granted the INCHI key is the correct INCHI key for the INCHI. So we recreate the INCHI key from the INCHI to make sure that the source has created the INCHI key correctly. We also have an arbitrary cutoff of greater than 2,000 characters long for a standard INCHI. The process for loading data into UniChem is now almost completely automated. Source-specific downloaders and parsers periodically draw and poll for data in different sources, put them into a common format, and then they're loaded by a single loader into a production database. And then there's a weekly release process. So the public data that you see on the UniChem website is refreshed every week. Occasionally, due to maintenance issues, this may lapse to 2 or 3 weeks, but we try to stick to 1 week. Similarly, with the associated downloads and mapping files, which I'll talk about in a minute, they're refreshed weekly as well. And the overall process is controlled by cron tabs. So now let's look at the current content for UniChem. So in the navigation pane of UniChem, if you look at the top level stats page under the analysis tab, it'll take you to this page here. And here you can get a very simple and quick overview of the release number, which is 51, the total number of structures which are in UniChem, which is currently just over 90 million. This is the number of records in that structures table. The total number of assignments, 188 million. That's the number of records in that cross-references table. The number of sources is 28. And if you want to see what those sources are, go onto the Sources tab in UniChem application, and you're given a list of all the sources that contribute to UniChem. together with a description, a short description of that source, and a simple description or summary of the process of data acquisition. So there are a number of downloads available as well. If you were to click on the Downloads tab under General Information, it'll take you to a page which points you to the FTP site. There's also a little description there of what the FTP site contains. Let me just take you to the FTP site. If you go there, this is what you see. There at the topmost level, there's a KNIME and data directory. I'm not going to talk about the KNIME one at the moment. That's full of KNIME protocols for drawing information from UniChem. You're welcome to explore it. But the data directory is what I'd like to drill down on now. If you drill down on that, you'll see what you see in the bottom panel to this slide, where there are two directories, Oracle Dumps and Whole Source Mapping. If you're to click on, let's look at Oracle Dumps first. If you're to click on Oracle Dumps, then you'll be presented with something which looks a little like this, which is a list of the UDRIs, or UniChem Data Release IDs. These are the same thing as the release numbers which were on the stats page 3 or 4 slides ago. I really ought to normalize them to the same name, but you can use them interchangeably. If you were to drill down on one of those, then you would see the contents as follows. Within there is an Oracle dump file, which is unichem.dmp, but there's also a series of files which represent the tables from that dump file, all as tab-separated files, compressed. You'll notice the cross-references table, the structure table, source and release table. There's a couple there which I haven't talked about yet, the labels table and the first entry key hash block hierarchy table. I'll talk about those a little bit later when I talk about connectivity search. There's also an MD5 checksum file which I recommend people use because some of these files are extremely large and there is a significant risk of corruption during the download process. So that was the Oracle Dumps directory on the downloads site. If we go now to the whole source mapping directory, if you drill down on this, then you'll see that for each source in UniChem, there is a separate directory. Each source is assigned an ID which is an integer, and you can see here there's a separate directory for each of those sources. If I'm to drill down on one of those, you'll see a series of files which represent, which contain the mappings between that source and all other sources within UniChem. So just to make that really clear, if I open up one of those files, I see something like this. This is the mapping file for source 3 to source 15, which is actually PDBE and ChEMBL. And you can see there's a big long list of all the mappings between all the PDE identifiers and all the ChEMBL identifiers. So as I said, these files are refreshed as often as necessary. It's not always necessary to do it every week because some of the sources in UniChem are not updated because they're essentially static because we can't get hold of the data anymore. E-molecules would be an example of that. We managed to capture the data before it became a private enterprise. So not all of these files are actually always updated on a weekly basis because they don't need to be. Analysis section, I'm going to talk through this. I've only got 2 or 3 slides on this, and I want to go through it very quickly because it's a bit of a distraction to what we're talking about here, but it is a large part of the UniChem site, so I just wanted to mention it here. So when we make the release, we run a series of analyses on UniChem content, and we largely do this for our own purposes to do some internal checks, internal tests on the release. But we thought it might be of interest to some users to also see these data, so we put them on the site. When we do these analyses, we look at the number of overlaps that exist between different sources and the number of structures from a source which are unique to that source and which are not owned, as it were, by or owned by any other source within UniChem. But when we do those analyses, we do that on the basis of defining structure in 3 different ways: either the full entry key, which is abbreviated to the FULIK, or the first entry key hash block, which I mentioned earlier, or something called the SCFIB, the separated single components of FIKHB, which is where we separate separate out the InChI, and then calculate all the first InChI key hash blocks. So there's essentially 2 pages which show these uniques and overlaps on the basis of those structural definitions that I just described. This is the structures by source, which gives the unique numbers for each source. I'm not going to go through it, but you're welcome to browse the data, of course, on the website. There's a detailed table legend which will give you far more information. I hope it's fairly self-explanatory. The second page is the overlaps page, which on this page there's a 2D matrix giving the intersect of all sources within UniChem against all other sources. Percentage overlaps and other different parameters are used. Anyway, I'll leave that for people to browse. Okay, so the last major section here is the connectivity search. And I'm going to switch the style of my slides here because the UniChem connectivity search was actually funded by Biomed Bridges, an FP7 project. And UniChem connectivity search is an advanced use of UniChem which permits searching across UniChem data sources for molecules which have the same molecular skeleton, the same molecular backbone or connectivity as the query, but can exist in different stereochemical or isotopic forms and or different salt forms or mixtures. So just to recap, of course, the standard way of using UniChem is creating on the basis of complete identity between full InChI keys. And the aim of the connectivity search was to create links on the basis of common connectivity. Again, the same requirements were needed. It has to be fast, it has to load when a web page is loaded. And it also has to identify relationships between molecules. It's not sufficient to say that this has the same connectivity, but we wanted it to say it is an isotopic variant of the query molecule as well. And we want to be able to link between compounds within salts and mixtures. And it had to be generic, flexible, and customizable for everybody to use. So there are alternative ways of considering molecular equivalence, and sometimes molecules that scientists consider equivalent in the context of their own particular field are quite often depicted differently across different resources. So frequently these depictions have different standard InChI, so that we can't integrate them using this matching standard InChI key. So just to emphasize that, consider these 2 compounds here. This is a neurokinin 1 receptor antagonist called CP99994. In ChEMBL, it's shown by the structure at the top, but then in PubChem, there's a similar structure which has 2 tritium atoms substituted on the right-hand ring. Now, if I was a pharmacologist, I'd be very interested, and I had some Ki information perhaps on the first one, I'd probably be very interested also to know if there is any KD or any other parameters calculated for the other version, for the isotopic version. But using UniChem as its standard way, I'd have no way of connecting the 2 together, and I wouldn't know about the second one. Similarly, paroxetine here, 2 different stereochemical forms of it. I don't know which one is the correct one myself. They might both be wrong. I'm not a chemist, but in a sense that's not important. If I was in one particular source looking at one of those structures, I'd want to know about the existence probably of the other one, and I want to know that there was a stereochemical variant form of it in the other resource. Well, using the first InChI key hash block shown in blue represents a fairly obvious mechanism by which we can connect the 2 together. But linking between mixtures and salts is a little bit more different, because here, of course, the connectivity layer is created from all the atoms within the molecule of interest. So yohimbine and yohimbine hydrochloride have different connectivity blocks. So we can't use that simple mechanism if we wish to link between mixtures and salts. However, the designers of the standard InChI were very clever in many ways, I believe, because they encoded mixtures and salts within a standard InChI in a way that can allow you to simply parse out the separate component InChIs. So here's an example, coamoxiclav, which is a mixture of amoxicillin and clavulanic acid. And you can see from the red and the blue how the two are essentially merged into one in the INCHI for the mixture, and how simple it is to parse out the two. The layers are separated usually by semicolons, or in the first layer I noticed by a full stop. So it's a relatively trivial matter, going back to our example of yohimbine, to parse out those two separate forms and then recreate the separate INCHIs from the separate component INCHIs. And then we have our mechanism back, which allows us to link between yohimbine and yohimbine hydrochloride via the parsed yohimbine hydrochloride form. So we can use that first INCHI key hash block as a mechanism for connecting structures via connectivity search, but we need to store those parent-child relationships of those first INCHI key hash blocks. So as we load new structures into UniChem, if it's a multi-component standard INCHI, we parse it and the separate first INCHI key hash blocks are generated and stored in the parent-child fields of the first INCHI key hash block hierarchy. And we use this table as a lookup if we wish to pull out data across mixtures and salts. You'll also notice we've added an extra field to the structures table called the FIKHB. So, using this principle, we can now map we can use the first INCHI key hash block as a way of pulling out of the database the connections which we're looking for. And once we pull them out, we can pull out the standard INCHIs as well. And then when we compare the standard INCHIs, the different layers in the standard INCHIs, we can effectively develop from that the different relationships which must exist. So if there's a difference in the isotopic layer of the two standard INCHIs that we compare, then we conclude that there must be a relationship is isotopic variant of. As I said, we can do a lookup in the table of the first INCHI key hash block hierarchy to do the same thing for salts and mixtures. And we can do all the different possible permutations and combinations of those as well. So how do we run a connectivity search? Well, in essence, it's very similar to running a standard search in UniChem. If you go to the connectivity search page, put in, say, ChEMBL 12 or your query term, or you could put in a structure. It'd have to be an INCHI key. And then if you submit query, then you will then run a query which does not use that first INCHI key hash block hierarchy lookup. In other words, you're not looking within mixtures and salts. You're just looking for stereoisomers and isotopic forms. But if you wish to extend the query to looking within mixtures and salts, then you need to click on the bar at the bottom, which is used to refine your query, which I can show you here, and then need to select from component C mapping, section C component mapping, option 4, which will allow you essentially to run all the different ways that you can to read across that first INCHI key hash block hierarchy table. And running that sort of query then often pulls back a very much larger data set than you would normally pull back for a UniChem query. And this table of data which is brought back is essentially very similar to the one for the normal search, which I showed you right at the beginning, except there's some extra columns in here. Most notably are the columns headed up with single letters towards the right-hand side, P, B, T, M, S, and I. These are the different layers of the standard INCHI. And the zeros and ones within those columns indicate whether there is a difference between the standard INCHI which has been retrieved and your query standard INCHI. So for example here, ChEMBL 10347 differs in the T and M layer to the query molecule. So you can run that same query by a web service. The details for the how to run that web service are quite involved, and there's a full documentation page on this on the link I'm now showing you. and it will bring back a similar data set. It looks very complicated data set. Essentially, in this data set is all the information that you saw in the tabulated data set 2 slides ago. If you look closely, you can see the B, I, P, and S layers, all indicated by zeros and ones. We did consider decoding those ones and zeros into relationships. So if there's a difference in the I layer, it would indicate that is isotopic variant of. But we resisted doing that and just left it at ones and zeros because we believe that users would want to put their own interpretation on different combinations of zeros and ones and their own formatting and so forth. So people are welcome to use the UniChem connectivity search. The developers of ChEMBL already do. If you go to the ChEMBL compound page, as we did right at the very beginning, you'll notice there is a link there which says view UniChem connectivity matches for the compound of interest. If you click on that, it'll give you that same data set which I just showed you two or three slides ago, all in a tabulated form, with exploring the differences between the molecule of interest and molecule in different sources. So just before I finish up, I'd just like to point out that you can train online with UniChem. If you go to the URL below, I understand this will be live within the next few days. This is a process where you can just walk through some examples of how to use UniChem all in your own time. It should take about half an hour to go through some of the examples in there. And lastly, some acknowledgements. This is largely a ChEMBL project, but we've been very grateful for help from KEBI, Atlas and PDE people, and I'm also indebted to my colleagues in training, Tom and Richard, who have helped out with the technology today. And now I think if there are any questions, I'll be happy to take them. There's a question here, can you use UniChem from R? And I'm afraid I don't know of anybody who's tried to do that yet, but and I haven't got much experience of R myself, but if from within R it's possible to create RESTful queries to the internet, then in principle I guess it probably is possible, but I'm afraid I'd have to find out more details of whether that's actually possible. Yeah, if anybody does have any more questions, or they think of anything in the next few days, please feel free to contact me. There's a contact email on the UniChem application, unichem@ebi.ac.uk. So please send me your questions. Okay, well, if that's it, there's no more, then I think we'll close. Thank you very much for listening.